Hey there, everybody. Mr. Mark with you, and today we're looking at black body radiation. So this is something that has been added in the 24-25 year to AP Physics 2. And we're not only going to look at the mechanics and kind of what we need to know at the end, but also kind of just a little bit of the history, why black body radiation was kind of an important thing in the beginning of the 20th century. So the first thing that we need to realize is that everything glows. All matter, no matter what it's made out of, spontaneously converts some of its internal energy into radiation. This is one of the ways that things can cool themselves off. So you're glowing right now as you're looking at this glowing screen. Most everyday objects, like you for example, emit radiation primarily in the infrared spectrum. So you would never notice that you are glowing unless we were to point an infrared camera at you or something like that. So being able to sense infrared radiation is one way that snakes hunt, and then that one Predator movie, that's how the Predator hunted. I'm not going to spoil anything besides that. So, what color do you glow? Generally, you emit a range of wavelengths, and that wavelength range depends on the temperature of the object. So, since wavelengths are pretty easy to measure, we've done that in class, or we may at some time. This is a really good way to measure temperatures. So that object shown is a infrared sensor that can measure the temperature of lots of different things. That's also the way that the thermometers at the doctor's office work these days. The ones they just swipe over your forehead. So they're just reading how hot you're glowing, essentially. So, in general, hot things are like red. It's like a stove glows red hot. Things that are hotter are like yellow and green, things like that. And then the hottest color would be the blue. So, as you increase the frequency of the emitted radiation, that indicates the temperature of the thing has increased. Another way to say that is that wavelength decreases. So, you can tell how hot something is just by looking at how the color that it glows. You can do that in astronomy. Like if you look at the radiation from a star, the temperature can be determined just by the frequencies of light that the star emits. A blackbody radiator is an idealized model of matter that is essentially a perfect absorber of radiation and a perfect emitter of radiation. If a black body is in equilibrium, that means has the same temperature as its surrounding, that means it has to be emitting radiation in order to maintain thermal equilibrium. So kind of a stylized diagram will look something like this. Whatever is falling on the black body radiator, regardless of the wavelengths of light that it is, it's going to emit a continuous spectrum at a specific range of wavelengths. So, at the beginning of the 20th century, we kind of figured that we had physics kind of well figured out, and that the only thing left to do was to refine what we knew and measure constants to more precision and things like that. But there was this lingering problem that was referred to as the ultraviolet catastrophe. So classical mechanics predicted pretty accurately the wavelengths of radiation from a black body radiator and their intensity for normal ranges of wavelengths. But what happened with the equation is that as the wavelength approached zero, or the ultraviolet spectrum, then the equation indicated that the intensity went to infinity. It's like it would produce infinitely more light, which is not possible. That violates any energy conservation, and y'all know you just can't violate energy conservation. And so everything that we knew about physics up until the year 1900 indicated that there was no answer to this catastrophe. Like classical mechanics predicted something that just was not observed in reality. And so a graph of what the radiation or brightness on the y-axis versus the wavelength looks like is something like that, where you have this nice gentle curve and there's a peak. We'll talk more about that peak later. And what classical theory indicated was that as you move to the left on that graph towards lower wavelengths or more energetic wavelengths, the intensity went to infinity, which again, just not possible. So, circa 1900, this German feller by the name of Max Planck derived an equation that didn't violate energy conservation and correctly matched the data that was collected. And what he did was referred to as the quantum hypothesis. We'll get into that here in just a second. At the time, he didn't really think that there was any underlying truth to the quantum hypothesis. It was more of a mathematical thing that fit the observation. So it's more of like, let's fit this data to what we, or fit our model rather to our data, more so than trying to overturn everything that we knew about physics. And so, kind of, generally summarizing at a very low level, the fix that Max Planck applied. So, classical mechanics predicted that radiation was emitted by things, today we might call them electrons, moving within the atom. And there was no limit on how fast electrons can move. Classically, there's no reason an electron has to have any specific range of speeds. Electrons in an atom can go as fast as they want to, classically. So what Planck introduced was the idea that those electrons that are moving within atoms are only allowed to have certain specific energies. And each electron releases a single piece, packet, photon, corpuscle, whatever you want to call it, of light when it lost energy. And that's where the famous equation E equals hf started. And so he didn't think that there was anything meaningful beyond that. It was just a trick that made the equation fit the data. So Planck eventually organized the first Solvay conference, which was a gathering of notable physicists that tried to make sense of all the things that have been happening after 1900 and Planck's hypothesis. So famously, Einstein, who's the arrow on the right side there, used Planck's quantum hypothesis to explain the photoelectric effect. And so upon his explanation of the photoelectric effect, quantum mechanics was born as a field of study, and Planck was eventually very instrumental in putting together some of the big pieces regarding the entirety of quantum mechanics, as it was known in the early 20th century. So kind of revisiting our graph here, and I've kind of relabeled the y-axis there. Let's just call it brightness, intensity. The peak on each of those plots, which represent different temperatures, is the peak or maximum wavelength, and that determines the color you perceive a glowing body to be. So for instance, our sun glows yellow. That's the frequency of light we perceive the most, and so that tells us what temperature the sun is. So if we can measure those wavelengths, then we can figure out what the temperature is. And the way that we do that is with a law known as Wien's law, where the maximum wavelength, I should say the wavelength that is emitted at maximum intensity, is equal to some constant divided by the absolute temperature. And the constant 2.90 times 10 to the negative third, and it's in units of meters times Kelvin. So when you divide that by Kelvin temperature, you get a wavelength in meters. So that can allow you to convert from temperature to the wavelength that's most noticeable about the radiation, and vice versa. And then the second rule that governs blackbody behavior is the Stefan-Boltzmann law, which describes the intensity or power at which a blackbody emits radiations to its surroundings. And so P equals A sigma T to the fourth power. So that red symbol is the lowercase sigma. In physics, you've dealt with a lot of uppercase sigmas. That's a lowercase sigma. That's actually used for quite a few different constants. A is the surface area, which we measured in square meters. Sigma is the Stefan-Boltzmann constant, 5.67 times 10 to the negative 8. And then the units are watts per meter squared, Kelvin to the fourth power. And then T is the absolute temperature, so again, measured in Kelvin. So that fourth power thing makes this one noticeable because we don't really see things raised to the fourth power very often in kind of first and second year physics like we are right now. And so that allows us to relate the temperature of an object and its area to the amount of power or brightness that light that it emits. So in class we will kind of practice applying both of those relationships, but that's kind of the nitty-gritty of what we really need to know about black body radiation. Thanks for checking this out. As always, ta-ta.